So let's talk about sampling. This is a tricky thing. Here's the definition. We've got this x of t. This is a continuous time signal. And we're going to sample every t sub s. You know that t is like a period, so this is our sampling period. Every t sub s seconds. If t sub s was equal to 1/2, then we'd be sampling every half second. And out is our discrete time signal. And now, with just a little bit of thought, we can say that our discrete time signal, therefore, has to be equal to x at n sampling periods. And that is something that's really important. When you see it, I want you to in your mind's eye see that we've got our original waveform here, and all we're doing if we're sampling it is sampling it at, here it might be every 1/2 seconds, so therefore t sub s, this would be 1, this would be 1.5, so therefore t sub s is equal to 0.5 seconds. And that would mean our sampling frequency is always going to be 1 over our sampling time period, which would be 2 hertz. So far, nothing surprising. Here's the surprising part, that there is a limited frequency range. Our limited frequency range says that in continuous time, our x of t, which we said looks like cosine of capital omega naught t. Omega naught t could be anywhere. But in discrete time, that is not true. And let me give an example, a really simple example to show why that's true. It doesn't get much simpler than taking an example of x of n is equal to cosine of 0 times n. So for this example, we're going to use omega naught equals 0. So for this, our sequence, let's see, when n is 0, we have the cosine of 0, which is, Charles?
1.
Mm-hmm. And then when n is 1, we still have cosine of 0, which is still 1. And so I'm going to simplify that for you. Let's give another example. That was a pretty wimpy example. I'm going to give the same example, but omega naught is going to be equal to pi here. What's our x of n here? So our sequence, our different sequences, pi times n. Nick, what's our sequence here? What is it at 0? For n equals 0, we've got cosine of 0. Actually, Charles already answered that. It's 1. What do we get when n equals 1 here?
That would be -1, sir.
Yeah. And then continue on. What would it be when n equals 2? What's cosine of 2 pi?
1.
Yeah. And then it just repeats.
-1, 1,
Yeah.
-1.
On forever. So this is the lowest possible frequency. And this is the highest possible frequency. This is omega naught equals 0 and omega naught equals pi. And can you see why you can't get any higher frequency this intuitively? This changes its phase 180 degrees every sample. You can't do any more than changing your phase 180 degrees. Just like I have a friend who's a brilliant salesman for IBM, makes tons of money, and he once said, man, that argument was so amazing. It changed my mind 360 degrees. Well, he's not a numbers guy. Obviously, that didn't change his mind at all, because you can only change your mind pi 180 degrees. That's the most you can change it. If you were to try to change your mind by 360 degrees, if you were to try to put in a frequency of 2 pi, then Kevin, what is your, oh, we've got 2 Nicks. No wonder that's causing confusion. If you try to put in a frequency of 2 pi, Nicholas, what would be your, what's your sequence now? What is it for n equals 0? Well, that's easy. That's still cosine of 0, which will always be 1. But what happens when we put in n equals 1? What do we get?
Would it be 1?
Yeah. And then what would it be for 4 pi when we plug in n equals 2? Let's go cosine of 4 pi. Yeah. And so now we're right back to where we started with. So there's no difference for omega naught equals 2 pi, then omega naught equals 0. It's the same thing. And if we did it for 3 pi, spoiler alert, it's the same thing for omega naught equals pi. We'd end up with this thing again.